Swayam Prabha. Digital India. Educated India.
Hello, welcome to another lecture on Introduction to Machine Learning. Today we will talk about a very important topic, which is linear regression. This topic is foundational for many of the advanced models that we will analyze in machine learning. However, advanced models, they are applicable to specific situations, and some even more advanced models keep getting invented every day. However, linear regression being a foundational topic is very important to understand because it gives us insights into how to analyze some of the more advanced models. So the objectives of this module are that the student should be able to write the objective for the regression function, and the student should be able to decompose the loss function of a regression equation into its bias and variance terms. We will talk about what is bias and variance, and also write the objective of the linear regression function. And then the student should be able to derive the analytical solution for linear regression and find what is the problem with the analytical solution and develop a computational solution which will lead to the same answer but which will be computationally efficient. Additionally, there will be advantages of using this computational solution, that we will be able to easily add regularization terms, and we will look at what is regularization also in this module. So linear regression sounds very simple, but we will also look at how linear regression is applicable in situations where we actually require a non-linear solution. So the outline will be as follows. We will start with the general regression problem, and we will look at its bias and various decomposition. Then we will get into linear regression, problems with linear regression, analytical solution of linear regression, and then we will look at the computational solution of linear regression, and then we will develop ways to regularize the computational solution. Okay. So the general problem setting for linear regression for regression is as follows. Okay. So let's say we have an input x, okay, and we will call it xi. Okay. So this is an input xi. Xi means it's the ith input, right? And with that we are given a target variable ti. Okay. So xi, I will write it as bold because it's a vector, and ti is a single value, it's a scalar. Okay. And this comes as a tuple, and there are several such values. So for example, we have x1 t1, x2 t2, okay, so and x is a vector, and up to let's say xn tn. So there are n such tuples for training. Okay. And what we want to do is we want to find a mapping from x to y, right? So we want a mapping from x to y, so so that this y is close to t, as close to t as possible. So again I will use the indices I. So we have the vector x, and we are going to estimate a scalar y, and this mapping will be based on some function f. Okay. So we have our xi, it belongs to d real numbers, it's a vector of d real numbers, whereas our ti and yi, they belong to a scalar, so it's just r to the power 1. Okay, so that's a general setting, and we want ti we want yi to emulate ti. So we want the function to come as close to ti as it can, and because of that it will reduce the error in the estimation. Okay. But we will see that there are other desirable properties of this function, and it should not always try to reduce the gap between yi and ti, and that is where understanding the bias variance decomposition will be important. That is where generalization in machine learning is important, because we don't want to be learning the mapping by rote and remember everything, every value of ti by rote by using a very complicated function. Okay. So first let us develop a loss function for this. So what is a loss function? Loss function is basically a function that we will minimize, and by minimization we will bring this yi close to ti. So what is yi? Yi is your estimate and ti is your target value, and xi is input. Okay. So we will say that yi is equal to fxi, all right, and we want this to come close to the target as possible. So once it comes close to the target, it can go either above the target or below the target. We want to penalize both going above and below the target. So we will say that let us minimize yi minus ti, right, and we will take the square of that, and we will sum it over all values of I is equal to 1 to capital N, all right, and we might want to divide this by n so that it is an average value, right, and we might want to add a half in front of it. That is for analytical convenience, because we will be taking the derivative of this objective function. When we take the derivative, because we have the square, it will cancel out with the half. Okay. So this is going to be our loss function, so we will call it L, all right, and this loss function is something that we want to minimize. There are other choices for this loss function, such as we could have taken the absolute value of the difference between yi and ti as opposed to the square. However, we will see that this estimation, this driving down of the sum of squared or mean squared error, that has some nice analytical properties and interpretation, especially when we think that the residual, which is the error that is left, has a Gaussian distribution, and Gaussian distribution is quite a reasonable assumption in many practical situations. So this is called the mean square error, MSE. Okay, so this is the mean square error loss function, which you will see popping up quite often in machine learning. All right, now let's look at this loss function a little more carefully. So we will use concepts of probability to look at this loss function, and what we will start with is expected value of this loss function. Okay, and what we want is we want to minimize the expected value of this loss function. Okay, so this is a stylized E, and if we think in terms of probability, then basically we can express this as, and we will have to integrate it over all the probability distribution of x and the probability distribution of t. So basically this is going to be L and then joint probability of x and t, and then dx dt. Okay. So what does this mean? So let's first assume that x is a single dimensional variable. So in a single dimensional variable, what you will have is, let's say you have an x and t plane, right? So you have this plane where you have x here and then you have t here. So why would t have a distribution? So first of all, when we are looking at different samples, training samples, right? So let's say we are given several training samples. These are xt pairs. Okay, so every point represents xi and ti pair. Okay, so from here we can see that there is a distribution of both x and t, but more precisely what we can think of it as that the values that we are given, they are actually not very pure, in the sense that there is some noise to it. We have some um, we have some ideal underlying t, underlying value that should have come associated with x, but we don't always get it. So let's take an example. So let's say we want to predict, let's say t is your power consumption, right, and x is temperature. So we are looking at a city in which x is the temperature and there is a temperature range, and based on that we want to predict what will be the so that is, let's say, the mean temperature during the day, and T is the mean power consumption during the entire day. So we might want to do this to predict how much power to generate in the power plants that are supplying to the city. So we can think of it as that when we measure the power, maybe all readings haven't come in, so we had to estimate some of those readings. So because of that, the target value that we get to make a predictive model for this situation doesn't have exact values of t. Maybe some of the values of t are actually estimated, they are not exactly correct. So that could be one reason why the t values, the target values themselves are noisy, okay, and your the input values themselves can also be noisy. So because of this, we will have a probability distribution, underlying probability distribution over both x and t. Okay. The other reason that there could be a distribution is that every time we get we have the same temperature for different days, we may have different values of the target. That is possible because, let's say, for 2 days that had that same temperature, one was a weekday, the other was a weekend, and we didn't model that in x itself. So for whatever reason, we have a probabilistic view of, we want to start with a probabilistic view of both the input and the target. So now let's try to look at this expected value of this loss function further. So what is this loss? So we will simplify and drop the constants, and we will simply call it y minus t, okay, y minus t squared, right. So we had that divide by 2n, we will skip that, and then we have p of xt dx dt. Okay. Now what we want to do is, because we want to minimize this loss, we will take its derivative with respect to y and set it to 0. Now y is a function of x. Okay. What is y? Y, we write it as y is equal to fx. So when we take the derivative of this expected loss with respect to y, it's actually y of x. So then what we will get is, we will get this 2 integration y minus t, okay, pxt, and this is for a particular x, so dx doesn't matter, we will have dt, and this will, we want to set this equal to 0. Okay, that's how we will find the minima. And this looks like the loss is a convex function because it's a square quadratic function, so we can do this. All right. So what this means is that your ideal y is going to be integration of t pxt divided by p of x. Okay, that comes from that integration and dt. Okay. And what is this quantity? By Bayes theorem, we know that this quantity is the conditional distribution. So what we will get is, your y should be expected value of, if you take the distribution of t given x. So now this expression is quite important because it gives us some insights to us. The insight that it gives us is that the minimized loss, we can minimize the loss only if we have the estimator y, which actually gives you whatever is the estimated value of t given x, even if t is distributed. So let's pick one value of x, and in this value of x, if we take a slice, right. So on this slice there could be a distribution. Let me take a different color. Yeah. So on this slice, there is a distribution of t. Okay. So for example, the middle value here is most likely, and then the value drops off when I go either above or below that. So there is a distribution of t that is around it, right? And that is basically the measurement error that we were talking about. Now, even be that as it may, even if there is a distribution of t, if we take the mean value or the expected value of t given x, right, that is the best possible estimate for the estimator to hit. Y should come as close to this expected value of t given x as possible. Okay. But this estimator y will never come close exactly to the same value as expected value of t, because there may be some constraints. It may not be a function that has infinite capacity. We will talk about capacity at some other point later in the course, but to put it simply, let's say if we have a function, right? So we have x and we have t, and we have different samples of x and t, right? If we have a functional form for y, and that functional form is such that it can only model certain types of functions. So for example, it can only model a function like this, no matter how hard we try to fit y to t, right? So this is your yx, y as a function of x or fx, right? So it can only come so much closer to t. So there will always be a gap between y and t, right? So what we want to do is we want to analyze that gap. We want to analyze the expected value of the square of that error and see if we can decompose it further into terms that we can understand in terms of the modeling capacity and how much closer we can come to t, and later on we'll also look at the noise in t. So this y minus t whole square, we can write it as y minus expected value of t given x plus expected value of t given x, right? So we just added and subtracted the same term, okay, minus t, and we can take the whole square of this. Okay. So when we do that, right, so what we get is so we wanted to minimize that, right? So your expected loss will have two terms, will have three terms. When we expand this square, we will get three terms, and those three terms, one of those will be y minus expected value of t given x whole square. Okay. The other term will be this expected value of t given x minus t whole square, okay, and then we will have the cross term, which will be this minus of or sorry plus of 2 y minus expected value of t given x times expected value of t given x minus t. And then we will have this entire thing, and then we will have p of xt dx dt, right? So what we can see is that this cross term is going to evaluate to 0. So what we will have is we will have two terms, okay. One will be this y minus the expected value of t given x, and then we will have another term which is expected value of t given x minus t. So now all these are slightly different from each other, okay. So one contribution that we will get is from this term, which is y minus expected value of t given x whole square, okay, and we will take its expectation with respect to the data that is given to us, okay. because we can only, what is data? Data is basically the pairs of t and x that are dealt to us. We are not talking about now a distribution over t, we are talking about the actual values of t and x that are given to us. So that will be one term. The other term that we will get is this expected value of t given x minus t and the expectation of this whole squared. So we will get two terms like this. Now the first term is basically your modeling variance, right? So here it depends on how complicated of a model that we use, and that complicated model will bring y close to, as close to t, expected value of t as possible. And the second one will be that there is an inherent noise in the model itself, and that inherent noise in the model is because the training target that we are given to us, which is ti, which is part of d, that training target itself is not perfect, right? It is it can come close to the expected value, but it may be noisy. So there may be some noise that is associated in these measurements, and that will be in the second term. Now the first term itself, we can divide it further. Okay. So here what we have is actually, so we also have an expected value of y. Okay. Why is that? Because every time we change the data sample, we might have a slightly different model. So let me put it again, let me draw the picture again. So let's say we have this x and we have the target value t. Okay. So now we think that there is some error in the measurement in t itself. So because of that, let's say there is some underlying ideal t for every x. So because of that, we will have some fuzziness around that t. So that is number one cause of variance in the model. The other issue that we can have is that now from this underlying model, we actually will sample some t, because we cannot look at every possible t and x pair. So we will sample some of them. So we might get a sample here, a sample here, a sample here, a sample here, and a sample here, and so forth. Okay. So now this sample can change in another sampling. So let's say if we were to do another set of measurements, we might get another set of samples. Okay. So between these two types of samples, every time we estimate a function for y, that function is going to be different, and that function is going to be dependent on the data itself. So that so we will basically sample it from the data itself. So basically what we are saying is that your y is going to be dependent on x and the data, which means however the target values are sampled from it, okay, minus, if we look at its expected values, this is expected value of t given x. This is what we want to minimize, right? So we want to minimize this. Okay. So here we will try to simplify the notation a bit. We will call expected value of t given x, we will just call it h of x. H of x, the reason we use h is because it stands for hypothesis. Okay. So essentially what we will get is that we will add and subtract a term. Okay. So that term will be the expected value from, given the data, the expected value of y as a function of x and d. So this is different from the actual y. Okay. So the actual y is some ideal y, right, that we want to hit, and this, the second one, which is the expected value given the data, is the one that we will get based on some sample, and the sample could be, for example, the red samples that you see here or the blue samples that you see here. Okay. So because of that, this term now we can add and subtract this term in the middle, and what we will get is y of xd minus expected value given the data of y as a function of x and the data, this will be squared, and then we will have another term which will be this expected value given d of y as a function of x and d, right. And here we will subtract h of x whole squared, plus we will have 2 times the cross term. So the cross term will be this term times this terms without the squares, okay. So those will be here. So when we integrate that, the cross term will vanish and we will have basically these 2 terms that are left, the 2 square terms that are left to us, okay. So essentially your expected value of loss will have 3 terms, okay. One term will be the bias term or bias squared term, I will just call it bias. The other term will be the variance term, and the third term will be the noise term, okay. So these are 3 different terms. The first term that you will get, okay, is the expectation based on the data that we are given to us of y as a function of x and data, okay, minus the true the expected value of t given x, okay, square of this, okay, and this will be integrated over px dx. Okay. So this is the first term and that is the bias term, and the second term that we will get is this integration of expected value, again given the data, of y as a function of x and d, okay, minus the expectation of the same thing, y as a function of x comma d, okay, square, and this will again be px dx, and sorry, here it will be plus, and then the third term will be the noise term, which is the double integral of hx minus t whole squared pxt dx dt. Okay. So the derivation apart, it's important to understand the importance of the 3 terms because they give us very important messages. The last term, let's start with the last term. The last term says that t is not exact, okay. T is whatever is given to us, but there is actually an expected value of t underlying it, which means that there is some noise in the measurement. Every time we try to measure something, we may not get the exact same value of t, even if the value of x is fixed. So because of that, there is some variance even for a given value of x. So let's draw it out. This is x, and now this can be y or t, both are on the same axis, okay. So even though we are given these points, for any given value of x, there is actually a distribution around it, a distribution of t around it. Okay. So that distribution itself, okay, that distribution itself has a variance, and that basically defines the noise in the target values. We cannot do anything about it. That is just how we are, what we are dealt with. Now let's look at the first term. The first term is also easy to understand. There is some true underlying value, right, which is h of x, which is the expected value of t given x. Now the closer we can come to that, the lower our bias will be, right? So that is the lower our error of estimation will be. But that error of estimation will not be, that error of estimation will be measured only with respect to the data that is given to us. But now we have the second term. That second term basically tells us that the y itself can vary depending on which data we are dealt with. So anytime we have a different model, right? So let's say these blue points were the ones that were given to us, and because of that we get a model for y which is, let's say, which looks like this. Okay. Now on the other hand, if we were to resample the data and we were given a different set of samples, our model could be slightly different. So we could get this red line. Now for different subsamples of the data of, let's say, if we could get infinite data, we could have many subsamples, and we could have many different estimates for this function y. So all these estimates for this function y, they will vary slightly, right? If we don't have infinite samples, if we have a finite number of samples in D, they will vary slightly. So because of that variance, because of that varying of the function itself, because of different samples, you can expect that the y that you will learn for any given x and the data will not be the same every time, because every time your data is different. And because of that, we expect that there will be some variance in the model. Now because of that, because all these three terms are positive, what we will get is that if we increase the complexity of the model, right? So a complex model can decrease the bias. Okay. So it will keep decreasing the bias because it can fit more and more exactly to the underlying data, to the given data, and your bias will keep decreasing. However, so this is your bias. However, your variance will increase. Your variance will increase, and because of that, if we add the two, we will get some sort of a minimum. Okay. And that minimum is the ideal complexity for the model. The third term we cannot do anything about, so your total expected loss will still have some non-zero value, and that is because of the noise term, and that we really cannot do anything about, but we can definitely minimize the sum of the bias and the variance. Okay. So what does that mean? So what is this variance? So you can look at the, let's say that you get a different value for y for the green curve and a different value for y for the red curve. So every time you resample, how much can you expect the model to vary? If you can expect the model to vary a lot, right, that means it has a high variance model, and usually more complex models have high variance. We can see this by thinking about what will happen if we use, let's say, different degrees of polynomials to fit a set of points, right? So if we have a set of points, let me use two different colors here. If I have a set of points like this and another set of points from the same underlying distribution, if I have a set of points like this and then I use another I have another distribution, sorry, another sample of from the same underlying distribution like that. So what I was talking about was the variance of a model, trying to understand how the bias and variance differs, right? So let's take x on the x-axis and y or t on the y-axis. Okay, and let's look at two different samples for the same underlying data. So you could have a set of points that are like this, and you could have another set of points from the same underlying distribution that are like the red ones. Okay, so the blue and the red are from the same underlying data, same underlying joint distribution of x and t. Okay, but there are two different samples. Now for these two different samples, first I will try to fit a line. So if I try to fit a line on the red points, it might come out like this. Okay, and if I try to fit a line on the blue points, it might come out slightly like this. Okay. However, because it's a simple model, the chances are that the how much the value of y varies between two different models is going to be small. So we will have a small variance. Okay. But then the line may not fit the points very well. It may not come close to the points very well. So it may have a large bias. Now instead of that, let's say if this yx, so in the first case it was, let's say, mx plus c, which is the equation of a line. In the second case, let's say we have yx is equal to ax square plus bx plus c, which is a quadratic equation. In that case, now let me try to draw using two different colors. So I will use a dotted line. Okay. So here now let's assume that I have a blue parabola, and that parabola may look like something like, it's becoming messy. So let me remove the lines and now redraw the parabola. So let's say the parabola will look something like this. It will come close to the blue ones, and instead if I use the red points to let me draw and show the interplay between bias and variance to give an intuitive idea. So let's say we are going to draw a graph where we have x on the x-axis and y or t on the y-axis. Okay. And we could have two different samples. Okay. So let's take a sampling that looks like this. Okay. And let's take another sample that looks like this. Okay. So these two sets of points are drawn from the same distribution, and that distribution is p of x comma t. Okay. Just that we get two different samples because we have drawn from the same distribution twice. Now let's talk about what happens if I use a simple model versus a more complex model. So let's take a simple model where we will use an equation of a line, and your yx is mx plus c, but what we will write it as w1x plus w0. Okay. So this is equation of a line. The second model that we will use is slightly more complex, which is wx is equal to w2x square, sorry, yx is equal to w2x square plus w1x, okay, plus w0. Okay. So here it's a slightly more complex model, okay, and they will have very different behavior. They will have different behavior. Now let's assume first we are fitting the red points with the first equation. Okay. In that case, we will get perhaps a line like this, and when we fit the blue points, we will get another line. We might get a line like this. Oops. Okay. So these are two different lines. Now each of the lines by themselves, if the underlying set of x and t pairs are not on a straight line themselves, then each of the lines will not perfectly fit the data. So this model will have high variance in both cases, in both samplings, high bias. However, under repeated resampling, it's possible that we will the slope of the line and the intercept of the line will not vary that much, so we will have low variance for a simple model. On the other hand, if I use the second model, which is the parabola model, then what I can do is, let me get rid of this line, then I might be able to come very close to the blue points, and it's possible that for the red points I will be able to come very close to the red points, okay, much closer to the red points. So in that case, what I will have is low low bias, okay, but high variance. So this is for a complex model, and this will become more and more obvious when your models have even more number of freedom. What is the number of freedom? What the degree of freedom? What is degree of freedom? You can think of it as the number of parameters that have to be estimated. That's a rough way of calling degree of freedom or a capacity of a model. So if your model has very high capacity, then it will obviously come closer to the training data points that are given to us. But if we were to resample the training points, we will get a large variation. So if we have a complicated uh, polynomial, right, very high degree polynomial, then under resampling it will vary quite a bit, okay, it can vary quite a bit, and the variance can be very large, okay. So now let's pause for a minute and think about what message we are getting from this. The message that we are getting is that it's important to estimate the variance of a model, not just the bias. Don't always keep reducing the bias of the model. So question is, how can we estimate the variance of a model? That variance itself is based on this theoretical idea that there is an underlying distribution of x and t, and then that underlying distribution is repeatedly sampled, whereas we may not have that luxury to completely understand what is the probability distribution of x and t together, right. Yet what we are given, if we have sufficient samples, we can create subsamples, we can create repeated subsamples including those with replacement, so that we can have multiple estimates of the model for the same underlying equation. So if the equation structure of the equation, so whether it is a linear equation or a quadratic equation, we can repeatedly estimate it on a bootstrapped number of samples from the same data. So if I am given several x and t pairs, right, so I have x1 t1 all the way up to xn tn, all right. So I can repeatedly, let's say, sample a subset of it, let's say a subset m which is less than n, and on that I can repeatedly estimate the model y of x and see what is the variance in y for different values of x. Okay, how much does it change? Does it change very wildly? If it is changing very wildly, that means there is a issue with that. And the easy way to do that is to actually look at just the validation loss. So what we will do is we will look at the training loss, which is basically an estimate of just the bias, and as the model becomes more and more complex, the training loss will keep going down. So this is loss, this is on the training data, and then we will also look at the loss on the validation data. So loss on the validation data will probably keep going down, and at some point it will start to rise. Okay. So this point of minimum where the validation loss is the minimum is a proxy for the point where the sum of it's an estimate of the point where the sum of the bias and the variance is minimum. That's why we get this dip in validation loss. That's one way of doing it. The other way would be that we take several bootstrapped samples and see which model gives you the lowest error on average error or average loss on a bootstrap sample. Another way to do this would be to do k-fold cross validation. So you divide the data into k different folds, you train on k-1 folds and test on the kth fold, and then you shuffle the folds and see which structure of the model gives you the lowest loss on an average on all the k folds, and that structure of the model will give you the hyperparameters, which is basically the structure of the model. So once you get that, you can then re-estimate it on the entire data, and then you can be somewhat confident that it will work on a test data so long as it is also sampled from the same underlying joint probability of x and t. So until now we were looking at regression as a general regression problem. We did not actually assume any form of the regression model. We did not assume any form of y of x. Now what we will do is we will assume a particular form, specifically the linear form, and then we will try to understand what kind of solutions we can get for that linear form. Now before that, it is important to understand why the linear form is used. Okay, so the linear form is quite simple. So as you can imagine that it is as straightforward as the equation of a line, which is y is equal to mx plus c. But we will not use this form. We will use w's to denote weights. Okay, so what we will write it as is y is equal to w1 x plus w naught. Even simpler model would be y is equal to w naught, where y is just a constant, and that's the simplest model that you can have. But we will make it slightly more interesting so that it varies with x. So we will make it y is equal to w1 x plus w0. Okay, and the way we will write this is we will write it as y is equal to dot product of w and x. Okay, so we don't want to deal with w0 as a separate entity. So we will try to absorb it in the w itself. So before we can do that, we will express x with one additional term, and we will call it x dash. Okay, so here let's say if we have x is multidimensional, so we have x2, x1. We will add a particular number to it, which is 1, and now we will call this x dash. Okay, so this particular vector allows us to simply absorb w0 in the w vector. So your equation would become y is equal to, let's say if you have d dimensions, w d x d, w d minus 1 x minus 1 all the way up to w1 x1 plus w0 1, which is part of that x dash. So basically the form of the model that we will deal with is w dot product with x dash, or another way to write this is using these angle brackets, w comma x dash, or you can also write it as w transpose x. All these are interchangeable terminologies, notations that we will use. Now the reason we study this linear model is because it is analytically one of the simplest models, and it is very well understood. The math behind it is quite inspired from probability theory and linear algebra. So we can get ideal solutions for this problem given a set of data, which means we will also have a set of target values, not just x, and so we will have some target for the y. Okay, and the other reason we studied this is because it's the foundation for more complex models via things via concepts such as linkage functions and so forth. So to give you an example, let's look at different ways of looking at the linear model. So what we can do is, let's say we want to fit a polynomial model for a single variable. So instead of xd, what we will have x to the power d. So we will have x to the power d, and then wd plus x wd minus 1 x to the power d minus 1, right, all the way up to w1 x to the power 1 plus w0 x to the power 0, which is 1. Okay, so this can model a polynomial of x, and now we have a nonlinear function. So we can think of different ways of defining these dimensions of x, which could be, for example, powers of a single variable, or these could be some basis functions such as Fourier basis functions, or these could be kernel functions such as the radial basis functions. So based on that, we can model nonlinear functions so long as we have fixed functions that are extracted and put inside this feature vector x. So we will use x as a catch-all for not just multiple dimensions, but it could be multiple features as well. So now let's look at linear function and its one optimal solution. Okay. So basically what we have is y is equal to w transpose x. Okay. So this x is bold, w is bold because both are vectors. Okay. Because we have multiple dimensions of x, and those could be either derived from a single underlying variable by extracting powers or by extracting kernels or and so forth, or they could be genuinely different variables. We don't care at this point. We just are saying that y is a single dimensional variable, y belongs to r to the power 1, whereas x and w belong to r to the power d. Okay, d is the dimension. Now we have this, but we also have a target value t. Okay, and all these can have these indices I, because I ranges from 1 to n. We have n different training samples. Now here, keep that in mind that w will be the same for all training samples. That is the model. The model itself does not change between different values of I. Okay. So now basically what we have is we assume that this target value t is actually equal to y plus some noise. Okay. And we will assume some distribution for the noise. So what we want to do is, if we want to minimize the expected value of t minus y to the whole squared, we are actually minimizing the variance of the noise. So let's say if we want to minimize the expected value of t minus y whole squared, that is equivalent to basically the expected value of noise squared. Okay, so that is the variance of the noise. Now why is it the variance of the noise? Because we can easily prove that this noise better have a zero mean. If it doesn't have a zero mean, then we will not be able to minimize the sum of squared errors or the mean squared error between t and y. Okay, so that is basically basic math, that the noise has to be essentially zero mean. Now because it is zero mean, we don't worry about the mean, but let's look at the variance. Okay. So now let's assume that this noise has a particular distribution. So let's assume that this noise is actually drawn from a Gaussian distribution. Okay. For Gaussian distribution, we'll write this stylized n, and what will be the mean? The mean will be 0, and we will have some variance. Okay, and we will call it sigma square. Okay. So and we don't know what that sigma square is. We just know that we can estimate it, but we don't know what that is right now. But essentially, the best estimator that we will have for any given t is that something that will have zero mean. Okay, that is pretty much given. So now let's look at the probability distribution of t given x, okay, and some weights w and this sigma square. Okay. So what is, let's unpack this this expression a bit. Okay. What is the probability value of t? The probability value of t means that under this given model, right? So under this given model, what is the distribution of t, right? And what is the model? The model is based on the weights w, okay, and there is an assumption of an underlying variance of the noise sigma. And what is this capital X? Capital X is basically the entire data matrix. Okay, so the way we will write this data matrix is that this X is equal to so each, because x is a vector, we will arrange it in rows. Okay, so we will have x11 all the way up to x1d. This is the first data point, right? So here we have d dimensions of the first data point, and then we will go all the way down, and we will have xn1 all the way up to xnd. Okay, so we have n data points, and that data point is in the last row, and it is expressed as follows. So basically what we will get is, now what is y? y is how many dimensions? Y itself is n dimension, so y is n cross 1, okay. And the way we will write it is, it will have this X matrix which will be n cross d, okay, and times w, alright. So w will be this is, all of these are now vectors, even y is a vector here, so I am writing bold y, okay, and this is a bold x because it's a matrix, and this is going to be d cross 1. Okay. So basically this is what we are trying to estimate the w for this, so that we can reduce the sum of squared errors between y and t. Now t itself can be a vector because we will have the n samples for t. So what is our objective function? So first of all, let's see what our objective function is should be, okay. For that we will try to first take a probabilistic view, and then we will come back to this. So to take that probabilistic view, let's look at the probability of t. We want to maximize the probability of t given x. We want to maximize the probability of t given x, okay. And what is that probability? So now we will make another assumption, and that is the IID assumption. IID means independently identically distributed. So any t that we draw given x, that will be so it will depend on x, but it will be independent of other t's that we have drawn, and it will be identically distributed if we draw the t for the same two different t's for the same given x, okay. So the assumption of this IID is this IID assumption is quite important for unpacking this distribution, okay. So here what we will do is that now this is the t vector and this is the x matrix, okay. So here, because every t is independent of the other t, basically this expression will be equal to product of all the probabilities of I is equal to 1 to capital N, okay. Why? Because for each t the distribution is independent of other t's. Each ti, the distribution is the probability is going to be independent of the other tj's. So we will have p of ti, okay, given xi. Now it does not depend on other x's because it is identically and independently distributed with respect to other t's, alright. So now what is this probability distribution? So this is going to be, it's going to be a Gaussian distribution, okay, and the mean of that Gaussian is going to be precisely what we estimate, right. So that is going to be this W transpose xi, alright, and the variance is going to be the noise variance, which we assume to be sigma square, alright. So we want to maximize this. Now what is the formula for this Gaussian distribution? Right. So the formula for this Gaussian distribution is going to be it's going to be 1 over 2 pi sigma square root, okay, and then we will have e to the power, okay, or let me just call it exp, it's easier to write it that way, minus 1 over 2 sigma square, okay, and then I will have the mean, I will have ti, okay, minus the estimate of it, which is W transpose xi, okay, whole square. Now if I want to minimize this, I can also take the, sorry, if I want to maximize this, why do I want to maximize it? Given the model, I should have high probability for the values of t that I have observed, okay. If I don't get high probability for the t's that I have observed, then my model is not very good, right. It is giving me very improbable values of t. It will give for the given t is very improbable given the model, right. So I want to maximize this probability, and when I want to maximize a function, I can take a monotonic function of that function and maximize that. So I will take log of this and maximize it, because then I can convert this multiplication into summation and it's easier to deal with those summation, right. Plus the exponential term that you see, that will become something that is easier to deal with. So instead of this, I will maximize the log probability of P of t, t is a vector here given x, okay, and because of that I will let me neglect all the constants. So basically it will be equivalent to maximizing, okay. Finally what we will get is we will be maximizing the sum of, okay, I is equal to 1 to n, and it will be negative sign here, Ti minus W transpose Xi whole square. Okay. So what does that mean? So this because I have a negative sign, it will become a minimization. So basically this will be equivalent to minimize over what? Minimize over different values of W. Find the W that will minimize this sum of squared errors. Okay. So we want to minimize this for sum over all the training points. Okay. So that's how, with the Gaussian assumption around the residuals, with the Gaussian assumption around in the noise of measurement of t, what we will get is when we try to find the maximum likelihood model for linear regression, we will get something that will be quite easily interpretable as minimizing the mean square error or the sum of squared error of the training points. Okay. So now what we need to do is we need to take so let's call this the loss function, loss of W for any W, and if we take its derivative with respect to W and set it to 0, what we will get is the maximum likelihood estimate. So when we take the derivative and set it to 0, what we will get is the maximum likelihood estimate of W, and that will be precisely X transpose X inverse, okay, X transpose times T vector. This is the T vector. Okay, let's unpack it a bit. So here what we have is X transpose X, right. So what is X? X, the dimension of X is n times d, X transpose will be d times n. So this entire thing will be d cross d, and we will take its inverse, okay, and then it will be multiplied with something that is d cross n, and then we have n cross 1. Okay. So entire thing will be same as what we will get here, d cross 1. So these are the d different weights that we want. So the entire dimensions of the matrix multiplication check out quite nicely. But now there is something more to it than what meets the eye. So in general you will have n that is greater than d, okay, n greater than equal to d at least. Why is that? Because otherwise we'll have an underdetermined system where we have more unknowns than the number of equations. So if n is greater than equal to d, then we have an overdetermined system and we will not have an exact solution. What that means is that our error will never be 0, but the sum of squared of the errors is going to be the minimum. Okay. So we will find a solution where we will have the sum of squared of errors that is going to be the minimum, and that is precisely what we started out to do with this. Okay. Now this quantity, this X transpose X whole inverse times X transpose is called a pseudo inverse of X, right. You can think of it this way: if you have t is equal to x times w, if we pre-multiply both with x inverse, we would get the t back, right? But we cannot multiply with x inverse. X is not an invertible matrix, so we multiply it with the pseudo inverse of x, and that will give us, when we multiply that with t, we will get the maximum likelihood estimate of the w's back. Now there is a problem with this. Okay. The problem, so now we will talk about the problems in this analytical solution. Now if you look at this particular pseudo inverse, x transpose x inverse times x, right. So here we are inverting a D cross D matrix, right. So how many order, what is the order of number of operations required to invert this matrix? So if we do any kind of triangulation of the matrices or any other such analytical method, the order can be order D cubed. Okay, we will need the number of operations that are proportional to d to the power 3. Okay, that will be some, the function will grow as d to the power 3. Now if you have a whole lot of, if you have a very large dimensional matrix where this d is let us say 10,000 or something along those lines, then order d cubed is a very expensive operation to conduct. Also it could be that the rank of the matrix is close to, it's less than the full rank, and then you have numerical stability problems in inverting this matrix. With smarter methods you can go up to order d to the power 2.6 or something, 2.6, 2.7. Even that is quite expensive when d is large. So what we need to do is we need to find a computational method that can give us the same solution, but without having to do d cubed number of operations or order d cubed number of operations. Okay. And this is where what we do is we start to use gradient descent. So in gradient descent, first of all, gradient descent works only for convex problems, but it should be obvious that if you are minimizing the sum of squared errors, then it's a convex problem in W. Okay, it's a convex function of W. So basically what we need to do is we need to update W by taking, so let's say this is your previous W, we will take some eta which is a step size or minus rather, because we are minimizing, and we will take its the gradient of, with respect to W of that loss function, which is the sum of squared errors. Okay. And we will do this iteratively. Okay, so we saw this in one of the earlier lectures, that gradient descent leads to the minimization of convex functions. And here basically what we will get is when we compute this derivative, we will get that W, the update equation for W will be this step size, but here then we will have a sum over I is equal to 1 to n, okay, and we will have Ti minus W transpose x xi times xi. So this is n, this is d cross 1, this is d cross 1, and this is a scalar, so this is 1 cross 1, and this is again d cross 1. Okay. So always ensure that your dimensions match out. And this is nothing but the summation and everything else that you see is the negative of the gradient. So here the only thing that we need to determine is what is a good step size, and as we have seen earlier that if the step size is too small, we will require too many steps for gradient descent. If the step size is too large, then we will overshoot and we will actually increase the loss as opposed to decreasing the loss. So now that we know that linear solution to a linear regression problem is very easy to get either analytically for small problems or using gradient descent for large problems. Now let's look at how linear functions can model nonlinear functions. So here I will take the example of some basis functions. Okay, so let's say we have a nonlinear function, right? So this nonlinear function could be something complicated like this, right? And this is an underlying function. What we get are samples. Now the samples, let's say, that we get are the following x. So like let's say these values of x. Okay, so for each value of x, I get the value on the curve, and these are my training points. Okay. So what I can do is I can define a set of features that are nothing but kernel functions that are sitting on these locations. What is a kernel function? So what I will say is that for any given point, okay, I will assume that there is a smooth function, canonical function, that is sitting at that point. If the point shifts right, then the function also shifts right with it. If the point shifts left, the function also shifts left with it. Okay, and then I can increase or decrease the height of this function by using a multiplier, by using a coefficient. Okay, so now if I add all these shifted and scaled functions, I might be able to approximate this white curve. So let's look at this. So let's say if I fit a function that is like this, and a function that is sitting here like this, a function that is sitting here like this, and the same function scaled up that is sitting on this point and this point, and I add all of them up, I might be able to get a curve that is quite similar to the white curve. Okay, so here now what is my linear underlying basis? Underlying basis for any x is going to be, instead of x, I will deal with phi 1 of x, phi 2 of x, phi 3 of x, dot dot dot. So these are my dimensions. What is phi 1? Phi 1 is the first green underlying curve, phi 2 is the second green underlying curve, phi 3 is the third green underlying curve, and so forth. So what are these curves? So let's say this is going to be it is going to be something like exp. So if it has a Gaussian type shape, then it is going to be exp minus of x, so here it is x2, let me write it here. So phi j of x is going to be exp x minus, I will call this some mu. Okay, so I will call it mu j whole squared, negative of that, and then I will divide it by some 2 sigma square, where sigma is some fixed width of these kernels. Okay. So now I have, let's say, d such points, and for d such points I get d different phi's, phi 1 to phi d. So I will have up to phi d, and that will become my new dimension. So instead of one feature x, now I have d different features, and for each of these features I will have a different weight. So I will have w1 here, w2 here, all the way to wd here, and then w0 for bias, and I will add that up to approximate the given target values as a function of x. So instead of one dimension, now I have d dimensions because of the d kernels that I have. Other thing that I can do is I can take powers of x, which I mentioned earlier is a polynomial in x. Then I can take a Fourier basis in x, and then I can add the linear combination of the Fourier basis also. So basically just using linear regression, we can model a lot of nonlinear functions. Okay. So now let's talk a little bit about regularization of linear regression functions. Why regularization is necessary? So we talked about the bias and the variance in regression models, and one way to reduce the variance in the models is to restrict the freedom of the model. So restricting the freedom of the model has to be done judiciously. It has to be done based on the on some understanding of the data or understanding of the model itself. And one of the most common ways of regularizing a model is to restrict its weights from becoming too large. So a polynomial is a good example. So let's say we have y is equal to wd x to the power d plus all the way up to w1 x to the power 1 plus w0, right. So if I let these so let's assume that we have y, which is a polynomial, and it is wd x to the power d plus all the way up to w1 x to the power 1 plus w0 x to the power 0, which is just a constant w0. Now for this particular polynomial, if I let the weights become too large, then what will happen? That I will have a polynomial that can wiggle quite a bit, okay, and because of that, depending on what subsample of the data, underlying data I try, I can have widely varying polynomials where the variance of the model will be very, very large. Okay. So one way to restrict this model is to restrict the number of degrees, restrict the d, reduce the d itself. Another way to restrict this model is to say that what I want is, I want the sum of wj squared, okay, j is equal to 1 to d, to be less than equal to some value, let's say eta. Okay. So what I am saying is that if I look at the w space, mind it is not x space, it is not x and w space, this is w space. I will say, let's say wi and wj, okay, two different weights. Then the weights can be positive or negative so long as they lie in a ball, and the ball itself is determined by this constant eta. Okay. So the L2 norm of w is penalized. Okay, we want to penalize the L2 norm of w. Now this is an inequality constraint, and we also want to minimize the sum of squared errors between y and t. Okay. So the way we will do that is use something that is familiar to you, which is Lagrange multipliers for constrained optimization. So we want to minimize the unconstrained optimization, is that we want to minimize the sum of squared errors between y and t. We want to bring y as close to t as possible. The constrained part of it is that while doing so, we cannot have the L2 norm of w more than a constant. Okay. And what this will do is, this will reduce the variance of the model. And what is the right restriction, right level of restriction? We don't know that yet. What for that we will do validation or cross validation or bootstrapped validation, etc. Okay. So we will do one of those things to find out what is a good value for good extent of regularization, good how tight this ball should be, that we will determine using validation. Be that as it may, so now how we will put this into a loss function? The way to put this in a loss function would be, now that we have I is equal to 1 to n, okay, and here we will have Ti minus y, which is w transpose x xi squared, okay, and let's normalize it. We will call it this by 1 by 2, we will have this and then we can even have sum of squared errors, so we can have 1 by 2n. Okay. Alright, so we want to minimize this, plus we want to minimize some lambda by 2 times, so this lambda is from the Lagrange multiplier, okay, of, now we will have another sum of j is equal to 1 to d of w, okay, wj, we will take the mod of that and we will take to the power q, where q is equal to 2. And I will come to why we have a general q, why we are not saying we are just leaving it as 2. For this particular example, we will have q whose power which is equal to 2. So this is the L2 norm of w. So we are saying that the two things together should be minimized. So what is lambda? Lambda is your extent of regularization. If you have large lambda, then you can only have very small weights within a very tight ball, okay, very tight hypersphere of w, where we are looking at d dimensions, not just 2 dimensions. So we will have a very tight ball if we have large lambda. If your lambda is 0, then it will be as if the second term does not exist, and because of that you will have unconstrained optimization, unregularized problem that we have already looked at. So we want to minimize this, minimize over w, find good w vector that will minimize this. So how will we do this? So first let's visualize this. So let's look at the first term. So again, let's say this is the w1 and w2 space, some 2 weights, okay. I cannot draw more than 2 dimensions, so I will just say w1 and w2 space. Let's say there is a value of w that is optimal, so let's call it w star. This is the optimal value of w for the unconstrained optimization. This is minimizes, this is equal to argmin of w when we minimize sum of squared errors, right. So this is ti minus w transpose xi whole squared. We are minimizing this over all values of I is equal to 1 to n, and you can even take 1 by 2n here, okay. So if we minimize this, then we will get this w star, alright. And if we don't get this w star, if we use some other w, we will get slightly higher value of this loss, okay. We will get slightly higher value of mean square error. So this is your mean square error. So because of that, we will have some contours around it, right. So these are contours of equal error, okay. So as we go outside in this bowl, the error, the sum of squared error is increasing, alright. So this is for the the sum of squared errors. Now let's look at the regularizer. The regularizer says that we want to minimize the sum of squares of w's. So when will it be minimized? When we will have w equal to 0, it is at the origin. So its contours will be circles, isotropic circles, okay, that are centered at the origin. Now one loss is pulling w in this direction, the other term of the loss is pulling w in this direction. So we have two opposing forces, and where do they balance each other? They balance each other based on what is the value of lambda. So lambda is your trade-off parameter, lambda is trade-off parameter, and 0 is less than equal to lambda is less than infinity, okay. So or less than equal to infinity. So this is your lambda, the range of lambda, or another way to say is that lambda belongs to R plus. So when lambda is 0, then we will get w star. When lambda is infinity, we will get w equal to 0, not just 0, 0 vector, okay. So the actual solution based on lambda will be somewhere in between. So where will it be? So it can be easily argued that it will, wherever it will be, it will be at a point where the two contours are tangential to each other. So they have to be tangential to each other, otherwise you can go along one of the contours and reduce the value of the other term in the loss function. So the two opposing forces will be such that it will the minimization will be achieved at the tangential point between two contours of the two different parts of the loss function. Okay. So depending on the lambda, the contour will shift up or down, or the tangential point will shift up or down. So we will get a locus, that locus will look something like, will be on all the tangential points between the two, and it will go something like this. Okay. So your solution will be somewhere along this locus, and both terms are convex, and when you add two convex losses or two convex functions using a positive constant such as lambda, then the resultant is also a convex function. That's a property of convex function, and it can be easily proved using just the definition of convex functions. So here now we have all these possible solutions as the joint minimized loss functions for different values of lambda. Now which one of them is correct? The one that minimizes both the bias and the variance. What minimizes the bias and the variance together, we don't know. All we can do is we can check it on validation data. The one that gives the minimum error on validation data, or repeated samples, subsamples of validation data, or k-fold cross validation, that is the best value of lambda. So or the best empirical value of lambda, or the best estimate of lambda in some sense. So we will use this lambda as a hyperparameter, whereas w will be the parameters, and we will minimize, we will try to find that particular solution where the loss is minimized on the validation data. Now this q is equal to 1 is not the only possible, q is equal to 2 is not the only possible regularization. We will also look at another possible regularization where q is equal to 1, which is the L1 regularization. So basically what we are saying is that we are minimizing the L1 loss, sorry, the L1 norm of W. So here the contours will become slightly different. Again, let's look at W1, W2 space. Okay, and again your unconstrained solution, let's say, lies here, and it has these contours. On the other hand, if we are saying that we want to also minimize lambda times the L1 norm of W, we need to draw the contours of L1 norm being constant. So what is L1 norm? That will be, let's say, W1 mod plus W2 mod, okay, is equal to constant. When this constant is 0, we will get the origin. When this constant is something else, we will get this 45-degree tilted square or rhombus or diamond, okay, and basically your contours will be these 45-degree tilted squares. So again the solution will be where the two contours are tangential. So we need to, for different values of lambda, we will get different solutions. So for example here these two are tangential. Now something interesting happens when we take the L1 norm. Now let's keep expanding this, and we will find that there comes a point where the tangential portion actually sits on the corner of one of the squares. The tangential contours of the unconstrained part of the loss function, the sum of squared errors of the loss function, that contour will just graze the corner of the square. There is no corner in circle, so that doesn't happen for L2 norm, it only happens for L1 norm. Okay. So what happens at that point? So at that point one of the weights is 0, exactly 0. So basically that weight gets eliminated. That means that feature or that dimension of x does not matter in the final solution. So basically it is as as good as saying that we have dropped that feature. Now you might be asking at this point why these are elliptical and why the other ones are not elliptical, or why the other ones, the contours of LQ norm of W, why are they either circular or squares. See, if you look at the contours of Ti minus W transpose Xi, right, Ti minus W transpose Xi, and we will take the square of this, right, and we will sum it over I, right. So here the issue, this becomes exactly so this is elliptical because here we are looking at the shape of these contours depends on the covariance matrix of X. So if X has two different dimensions that are correlated with each other, these ellipses will be tilted as opposed to being aligned to the axes. Okay. So that is how it is, but it is still a quadratic function, that's why you get ellipses. Whereas when we change the penalization term, so the penalization term that we had plus lambda times, I am not using lambda by 2 here now, so we have this sum over j of W to the power q, right, and we can take the qth root of that also, so we will take the qth root of that. So that is your LQ norm, right. So here earlier we had this for to the power 2, here we will have for q will be equal to 1. Whenever we have this, then now the contours of the second term are not going to be circles. They were circles and not ellipses for q is equal to 2 because we were looking at same weight given to all dimensions of W. But now we are giving the same weight to all absolute values of W, not the squares of W. So we will get these squares. So once we have these squares, we have the situation where for a certain size of a square, for certain size of the square, the tangential point will actually graze the corner. The tangential curve from the error minimization will graze the corner, and because of that one of the W's is going to be 0. In this case, in this figure, W2 is 0. So the locus that we will get, okay, is going to be exactly 0 for W2 at until a certain point, and then it will go like this. Okay. So for a particular critical lambda, when you increase lambda further, when lambda is greater than a particular value, some weights can become 0 and those weights will remain 0 for higher values of lambda. So in that case what happens is that we do feature elimination. So another way to look at it would be that if we have uncorrelated dimensions of X, right, and we look at let's say what is the unconstrained weights. So this is unconstrained weights, and this is the constrained weight for lambda greater than 1. Okay. So if we have no lambda, then we get an identity function. If we get higher lambda, then for L2 norm we will basically be reducing the value of so this is no constraint, and this is some L2 constraint, L2 regularization. Why will the weights dip like this and dip in the absolute value like this is because we are trying to constrain the L2 norm of the weights. But what will happen for L1 norm, we get a behavior that is like this. We will have some reduction in weights, but then it will become exactly 0 for certain values, and then we will have another reduction in weights, and this reduction is constant so long as the data is uncorrelated, the different dimensions of x are uncorrelated. So here we will have a, for L2 norm we will have a constant factor reduction, so there will be an angular rotation of the weights in some the weight line, and in the other one we will have this dead zone sort of in between for large values of lambda, and outside that there will be a constant reduction in weights. So this is a behavior that we see for uncorrelated x for different types of regularization. We can also try other forms of regularization where, let's say, q is equal to half. I will leave that as an exercise, that the contours will be something like a square but that is like squished in, okay. And if q is equal to 3, then instead of circle we will get like a rounded circle where this distance is larger than the radius, larger than this distance, so it is like pushed out a bit. When you have q is equal to infinity, you will get a contour like this. So this is L infinity norm, q is equal to infinity, okay. And when you have q is equal to 0, then your it will be so much squished in that it will basically just, so this is q tending to 0. It will be squished in almost to the axis itself. So they have different behaviors on how they control the weights of the model. So I hope you have got a good picture of linear regression, how nonlinear regression can be modeled as linear regression, and how to constrain linear regression even if you have a lot of features, even artificially created features such as powers of x or radial basis functions or kernels of x. Even then, if you expand the dimension, you can still regularize the model using L2 regularization. L2 regularization is called ridge regression. So L2, you will see the term L2 is synonymous with ridge penalty or ridge regression. It is also synonymous with Tikhonov regression, and it is also synonymous with weight decay in neural networks. And we have L1 penalty. The L1 penalty is synonymous many times with lasso, linear shrinkage and elimination operator. I forgot the exact number. It's called lasso. It's basically a convex relaxation over the L0 norm. We use the L0 norm to eliminate some weights, and because that's not a convex function, we use the something called a convex relaxation, which is L1 norm. So with this, I will close this lecture, and I'll see you in the next lecture. Thank you.